So the question here was, of the following, which is the best model of flow and reactions in a river? Let's go back, and right here we've got a plug flow reactor. Okay. So thinking about a river, okay, here's my river. Okay, we have flow in the river. Okay, and if we're thinking about if we were to add a dye, then what's going to happen? Okay, we're adding, this is our parcel, so we're adding dye. As long as this is well mixed, this parcel is going to move down the stream. Now, in reality, we would have dispersion, but assuming no dispersion, this parcel is just moving down. So while we have complete mixing within this parcel, here, the flow in that parcel is actually moving downstream in a plug flow manner. So typically when we're looking at modeling flow in a river, we will use a plug flow reactor system for the description as it moves downstream. Okay. So just thought that was helpful to think about it. Now, it's somewhat mixed. Some of you did answer completely mixed reactors. So in the situation here, where let's say we have, I'm going to describe this as an outfall. So we've got a wastewater treatment plant, and we've got flow into the river. We will typically model this flow right here as a CSTR. So we'll assume we have instantaneous mixing at that point. But then once we have mixing, then the flow downstream will be plug flow. So hopefully that helps to identify some of the misconceptions and also correct those. Any questions about this? Feel free to write in the chat, or if you'd like to unmute yourself, because this is a really important concept.
So you said that was like a tributary or something, right?
To this diagram here. So for instance, this could be a tributary into a river. It could be a outfall from a wastewater treatment plant, an outfall from some sort of a manufacturing facility. So what we will do is we'll model that outfall as a CSTR. So for instance, this is my river, and then I have an outfall here. We'll model this mixing right here as a CSTR, but then everything beyond that, as that flows down, we'll model this as a plug flow. Questions? Because as I said, this is a really important concept. Not getting this at this point will lead to multiple confusion throughout the semester. Question, what's the difference between a CSTR and a CMFR? For all practical purposes, nothing. And what exactly is acting as the plug here? So basically, think about it here as we have this is our plug, okay? So basically we have continuous mixing. So we have this outfall and we have the river. And then I'm just going to try and change colors. So this here is going to move downstream as a plug. And if there's a reaction, okay, it is occurring within the system. So we're assuming no mass enters or leaves this plug. Okay. Does that help? Okay, so let's move on to basically where we left off on Friday. We had a reactor. We said that that reactor was filled with 500 cubic meters of pure water. And at T0, the pump was turned on, and we're pumping in a non-reactive salt solution that has a concentration of 100 milligrams per liter and at a flow rate of 50 cubic meters per day. And you're told that the volume of this solution is constant, in which case Q in equals Q out, which we can call Q, and that is 50 cubic meters per day. And you were asked to draw a picture, state your assumptions, and write a mass balance. And this is what we did on Friday. So we got to this point on Friday. We wrote an equation in mathematical terms. So we wrote it in words, we wrote it then in terms. And then what I drew was a model or a graph that showed the change in concentration with time. Now, I could have written this for mass versus time. Why, in this case, is mass interchangeable with concentration? I want to try and answer that in the chat. Why is mass interchangeable with concentration? So we have here the change in mass, exactly, because volume is constant. Okay, because here, change in mass with respect to time, and that's equal to dCV dt. It's change in concentration times volume. And since volume is constant, we can factor out volume. And in this case, and for all practical purposes, everything we do this semester, okay, we will assume constant volume. So mass and volume will be interchangeable. It's not true. If your volume is changing, it becomes a much more complicated situation. We need partial differential equations. We're not going to go there. ENE 801 is where you really start looking at. If you take that as either as an elective in your undergraduate program, or if you continue on for graduate school, that is where you would look at these more complicated problems. Okay, so as I said, we have our equation, wrote this. We said that Q in equals Q out equals Q. So we have this equation here. This is our mass in, and this is our mass out. And this is equal to V dC dt. And then if we integrate this expression, we're going to integrate it from C0 to Ct, and from time 0 to time t. And this is the general equation that we will achieve. Okay. Now remembering, we go back here to this example here, okay, we start out here with pure water. So C0 is equal to 0. So in the case that we have here, this term drops out of the equation because C0 is equal to 0. So the only part of the equation that we need is this first part of the equation. What if the initial concentration were not 0? And I realized something here. I'm just going to... Okay. So we have that previous equation that I just gave you. If we plot the data, so we're plotting T versus C. Note, initially we start with pure water in the reactor. Okay. And as we're pumping into the reactor, so here's our reactor. Okay, we're pumping in a solution that contains 100 milligrams per liter. So over a period of time, this is our non-steady So we have non-steady state conditions initially as the concentration is increasing, and then we reach steady state conditions here, and notice we're at 100 milligrams per liter. Okay. Now, what if the initial concentration were not 0? Let's say it is 50 milligrams per liter. So in this case here, we have a reactor. We start out with 50 milligrams per liter as C0. We're still pumping in 100 milligram per liter solution. We still have C out here. Q is still the same, and the volume is still the same. So we keep everything constant, except for the fact that in this time, we have a 50 milligram per liter solution in the reactor. What's the steady state concentration? Anybody want to venture to guess state? What would be the steady state concentration in this case? We still have the same equation. If 50 is possible, anybody else want to make a statement? Think about it. Okay, so it's going to be 50 here. Okay, Cn is 100, and we're going to plug in numbers. Okay, so it's just 1 minus exponential of Q is 50, D is 500, T is T value that we use, plus 50 here, exponential of minus Q minus 50 over 500, again, T, okay? So the answer is 100, okay? We start here now at 50, and that concentration will continue to increase. Think about here. Here's a reactor. We start at 50. Okay. We're adding 100. But basically, you're flushing the system out with this 100 milligram per liter solution. So what's in the reactor is also leaving. So basically, you're replacing that 50 over time with 100 milligram per liter solution, and it's going to continue to increase here over time, and then at steady state we end up with the exact same position, the exact same condition we had when we started at 0. So at steady state we will end up with 100 milligrams per liter. Now, what if instead we have a situation where now we start with 50 milligrams per liter as C0, but instead we flush out, we're flushing the reactor with a pure water solution. What's the steady state concentration now? Same equation, and you're absolutely right. And so we start with 50, we're flushing with the pure solution. So here's our reactor. We start with 50, we flush with a pure water. Okay, and notice the concentration is going to decrease with time until it reaches 0. So the steady state concentration is 0. And notice in all cases, the time to reach steady state is about 40 days. Okay. It's roughly, where we have no reaction, it's roughly 4 times the detention time. Our detention time, and how do we calculate that detention time? So volume is 500 cubic meters. Q is 50 cubic meters per day. So our detention time is 10 days. So notice here, in a general rule, you'll see that typically it takes about 4 detention times to reach steady state without reaction. If you have a reaction, that will change. But without a reaction, it takes roughly 4. So we've got to flush out the system, essentially 4 volumes, in order to reach steady state. What if we have a reaction? So here, let's just look at the reaction where we have some chemical A reacting with B to produce C. And we have the stoichiometric coefficients of A, B, and C. So A moles of A react with B moles of B to produce C moles of C. We can write an equilibrium, we can write a reaction rate expression. So the change in C with respect to D is equal to some rate constant times A and B. Okay. Now, M and N are not based on the stoichiometric coefficient, except in some very, very special cases. M and N are empirically derived. So you've got to obtain this information from the empirical data. Now, if the rate is only dependent on one reactant, let's say A, we can write a more simplified expression. We still do not know M unless we experimentally determine M. For those of you in 480, you'll actually do an experiment where you will determine the rate kinetics. Now, if M is equal to 1, then the reaction is first order with respect to A. It's 0 order with respect to B. And we can write an expression that says that the change in C with respect to T is equal to a rate constant and times the concentration, in this case, the concentration of A. Now, we've just written the same expressions, which I just gave you. Now, if A here is equal to C, then the rate of change in in C is equal to minus the rate of change in A. So as C increases, A is decreasing in a proportional amount. And we can write this expression that change in A with respect to time is equal to minus K times A. This essentially is the expression that we will use throughout the rest of the course to describe first order rate expressions. So many environmental reactions can be described with first order kinetics, or what we call pseudo first order kinetics, and that's where one component is in a much higher concentration than the other. So basically its concentration is essentially constant, so we can describe it as what's referred to as pseudo first order. Again, if you're taking 480, you'll cover that to greater extent in 480. I'm not going to go into details here. But now, going back to our mass balance, we have the same mass balance expression that we've had. Now we add a reaction term. Now we can describe this as either positive. So if it's positive, you have formation of whatever chemical you're looking at, or you can also use it for microorganisms. If it is negative, then we have decay. So we can write this expression. So this is our rate expression here. So this is our mass. This is our mass balance, and this is our kinetic expression. This, we replace this term here with this expression here, we end up with a term here, V times Kc. So it's the volume times the first order rate constant times the concentration. And this here is going to be the concentration in the reactor. I've put up another poll. As we talk about this, we've been talking a lot. So you should see the results. Okay. When your change in mass with respect to time is equal to 0, the system is at steady state. Okay. When we talk about equilibrium, we're talking about a chemical reaction. So for instance, there, if we look back at the chemical reaction we wrote for the general reaction, if this is at equilibrium, there's no net change in the concentrations of these species here. But if we're talking about, when we're talking about rate of accumulation, we're looking at a reactor system, okay, and we're looking at the change in mass in that system. So when the rate of accumulation, change in mass with respect to time is equal to 0, we're talking about steady state conditions. So we have our mass balance equation. if again, we'll assume completely mixed reactor. So we have the CSTR. So the concentration in the reactor is equal to the concentration leaving the reactor. We'll assume that the volume is constant. And we'll assume that the compound decays according to first order kinetics. So our K will have units of inverse time. So we can write our mass balance equation here. Our mass in is equal to Q times C in. Mass out is Q times C out. And because we have decay, this term is negative. It's a net loss. And we've said volume is constant, so we can factor out volume from the differential. Now, if we integrate this from C0 to C sub t, and from T0 to time t, we have this general form of the equation. It's more complicated than before because now note we have a K term in the exponential, and before this was just C in. Notice if you don't have a K, then the Q over V factors out. Okay? So where we have reaction, this is the equation we will use. So now, if we have the same problem that we had before, except now we have a substance that is degrading with a rate constant. Okay, so we start out with pure water, with clean water. So C0 is equal to 0. We're going to pump in, now we're going to pump in a reactive substance, same concentration as before. Flow rate is the same as before. And now the substance degrades according to first order kinetics, and we have a rate constant of 0.25 inverse days.
Professor Maston,
Yes.
can you go back to the previous slide?
But just note that, like I said, if you don't have K, then this equation is exactly the equation that we had before for a non-reactive substance. So if K is 0, it's the exact same equation. So we have the exact same system before. The only difference we have is that instead of a non-reactive substance, we have a reactive substance. So in this case here, how do you think the graph will change? How will it compare to the previous graph? Steady state concentration. Will it be the same as before? 100 milligrams per liter? Okay, so we have steady state will be at a lower concentration. It will slowly go down. Okay. Now remember, we start with a clean solution. So here's my graph, and I have concentration with time. At time 0, we have concentration 0, okay? So that instantaneous point in time as that pump is turned on. Before, it went to 100. It's going to be less. Okay. Let's look. Okay. So here, notice here, our steady state concentration is about 28.6 milligrams per liter. And the time that it took to reach steady state is much less than it was before. So before, it took about 40 days. Here, by 20 days, you've reached steady state. So let's just go back. I didn't include it here, but let's write the mass balance expression. So we have the change in mass with respect to time is equal to mass in minus mass out minus mass reacted. Since volume is constant, we can write volume dc dt is equal, and since Q, volume is constant, we'll use Q, so we have C in Q minus C out, Q minus K. This C is our C out, times the volume. And then when we integrate this from C0 to C sub t, and from time 0 to time t, we have the equation. I'm not going to write it out, the equation that I had before. And then we can use it. I just did it in an Excel spreadsheet. I can then determine the concentration at any time. So this is C at any time t. What if instead of having a pure solution initially, we have a 50 milligram per liter solution? So what we change now is we have a 50 milligram per liter solution. This is C naught. Same reactor. We turn on the pump. We're going to pump in the same reactive substance, 100 milligram per liter solution, just as before, same flow rate as we've used, same rate constant. What's the steady state concentration? Absolutely correct. So here we're going to start at 50. That's the initial, and it's going to decrease to the same concentration. And we're back to the same concentration. So here we are. So it starts here, decreases, and it's 28.6 milligrams per liter. So this was a situation where we had no reaction. Here we start, C naught is equal to 0, and we're pumping in 100 milligram per liter solution, and the rate constant is 0.25 inverse days. Here we start with C0 equals 50 milligrams per liter. Same situation. Same reactive substance that we're pumping in. And we end up at the same point. What if the initial concentration were 100 milligrams per liter? So what if instead we have, let's just add another one, okay? So C0 is equal to 100 milligrams per liter. So if we start out here we will end up with the same concentration right here. I want you to think about that. I'm going to stop here, okay? I want, between now and Wednesday, I want you to think about that. Okay. So the steady state concentration is independent of that initial concentration in the reactor. What? It's dependent entirely on what you're pumping into the reactor and the rate constant. Think about that mathematically. Okay, we can go back. You've got 0 equals your mass in minus mass out minus the mass reaction. Okay, think about that mathematically. And think about that physically. What does that really mean? And how is that going to affect our systems? For the most part, in water and wastewater, we operate at steady state. We actually don't care about the initial condition for the most part. I'm going to leave you with that. And if anybody has any other questions, happy to answer them. We'll finish reactor theory tomorrow. We'll do a few more problems like this. We will have some group assignments, so be prepared. And until then, have a great day.